Hi, my name is Nikhil and I'll be talking about a paper on learning socially appropriate robo-waiter behaviors using real-time user feedback. Let's get started. Humanoid service robots are becoming more and more prevalent in the hospitality industry, whether it's conducting deliveries to guest rooms, being robo-waiters taking customers' orders, or delivering food to their tables in restaurants and cafes. HSRs are donning more active roles in serving humans in daily interactions. To effectively navigate in human environments, these robots need to learn behaviors that are considered socially appropriate by humans. This may include navigating in human environments, learning appropriate approach behaviors, navigating through complex real-world home scenarios, or as robo-waiters facilitating customer orders and assisting them in service settings. In this work, we focus on one such setting where we evaluate Pepper as an effective robo-waiter navigating through a restaurant, learning socially appropriate approach and positioning behavior with respect to humans. For this, we simulate a restaurant environment by designing a 9x9 grid, placing the customer table right in the middle. The robot needs to learn how to approach the customer table and position itself appropriately to interact with the customers. One challenge in such settings is to determine what might be considered appropriate behavior. For this, we adopt a crowdsourcing approach to gather appropriateness ratings for robot behavior in our grid world scenario. For each position in the grid, we generate images or GIFs for that position and ask the participants to imagine being served by the robo-waiter from that position. These generated images or GIFs are presented to participants using Google Forms, where they're asked to provide annotations for the appropriateness of the robot positioning itself or speed, as well as their effective responses towards the robot being in that particular position. Each individual form is annotated by 8 to 11 unique participants. So what do these annotations look like? Let's look at positioning first. This grid shows the average appropriateness ratings on a scale of 1 to 5. We see that there's a clear preference for positions in front of the table. Furthermore, participants rate the robot positioning itself closer to the table as more appropriate, while positions behind the table are considered to be less appropriate. For robot speed, we see that appropriateness of the speed of the robot varies with its positioning. For instance, slow to medium speeds are considered more appropriate when robo-waiter is in front of the table, while faster speeds are considered to be more appropriate when it is behind. Finally, evaluating the effective responses of participants towards robot positioning, we see that the participants report a higher valence value when the robot is in front of the table, while higher arousal values are reported for positions behind the table. Looking at both arousal and valence together, we see that positions in front of the table, participants report positive valence with calm to neutral arousal, indicating that these positions are preferred. On the other hand, participants report low valence and high arousal, that is, feeling agitated or unhappy, when the robot is behind the table. Having collected these ratings, it is important to evaluate how reliable these ratings might be. For this, we compute the Fleiss kappa to measure the reliability of agreement between participants on these ratings. We split the grid into quadrants and compute these values for different regions within these quadrants. Overall, we see a moderate agreement between participants across different ratings. Position and valence ratings are more reliable with a higher kappa value compared to arousal and speed ratings. In particular, we see front right or quadrant 1 receive relatively higher kappa values compared to other positions. Yet, this agreement is still at moderate level, resulting in a lot of scope for allowing robo-waiters to consider person-specific adaptation while modeling interactions with them. To learn appropriate behaviors, making use of the annotations collected, we design a reinforcement learning problem where the top right quadrant is used to represent the restaurant settings. The action space for the robot in this environment is defined by moving up, down, right, or left at different speeds. At any given position and speed, the average crowdsourced appropriateness ratings are used to reward the agent to be in that particular state. To implement the behavior generation model, we compare 3 different reinforcement learning strategies. More details on these can be found in our paper. We train these different models with the collected data over 20,000 episodes and compare them in terms of the rolling episode score achieved by these models. As can be seen, DQN performs the best and is the most stable. Although A3C is the quickest to converge, it converges to a suboptimal solution, while DQN plus HER is relatively unstable. We train these models only using the position value matrix we saw in the previous slide, with no real-time adaptation in the model yet. To evaluate how we can learn and adapt behavior with human feedback, we conduct an HRI study with Pepper as a robot waiter. The restaurant grid settings are realized with Pepper interacting with the customer sitting at the table. We recruited 21 participants to interact with Pepper across 4 different interactions or tasks. Firstly, the Pepper welcomes the participants to the restaurant, takes their order from a menu of options, goes away and returns with their order, and finally returns to collect dishes and receive feedback. Since at the time of the study, COVID-19 restrictions were in place, no actual food or dishes were used, and instead the whole scenario was acted out with the participants. Each participant repeated the 4 tasks with the Pepper under 4 randomly ordered conditions. Thus, in a within subject design, the participants saw 4 different versions of Pepper performing the same tasks, one after the other. The first condition was the control condition, where Pepper randomly positioned itself throughout the 4 tasks. For the second condition, we used the pre-trained reinforcement learning model trained on the crowdsourced data to govern Pepper's behavior. For the third condition, we used pre-trained reinforcement learning as a starting point for the robot and let it adapt based on the explicit verbal feedback provided by the participants. And finally, we evaluate the facial affect of the participants, particularly valence, to determine their evaluation of robot behavior implicitly and use this to adapt robot behavior. Both C1 and C2 represent non-adaptive settings, while the robot adapts in real time with user feedback under C3 and C4. For explicit feedback, we evaluate the verbal feedback provided by the participants and quantify the reward given to the robot using a keyword spotting approach. For implicit feedback, we use an off-the-shelf facial affect recognition model to compute deviations in participants' valence measurements. The reward function was modified to include both crowdsourced appropriateness rating as well as explicit or implicit reward based on the condition assigned. This allowed the robot to adapt in real time to user feedback. With our HRI study, we aim to evaluate whether pre-training robot behavior on crowdsourced data actually improves its performance compared to static behavior. Furthermore, we wish to evaluate whether using explicit or implicit feedback improves interactions compared to using only crowdsourced data. And finally, is there any benefit of using either explicit or implicit feedback over the other? To answer these questions, we record participants' responses on questionnaires collecting ratings for enjoyment, sociability, adaptability, and appropriateness of robot behavior. And these evaluations help us understand how individuals view their interactions with robots. For enjoyment ratings, we see that adapting with explicit or implicit feedback results in overall improvements. Pre-training also on average improves over using static behavior. For sociability ratings, we see that an overall increase in ratings across dimensions under pre-trained or adaptive conditions. In particular, using explicit feedback significantly increases the sociability of the interactions. Adaptability ratings show a similar trend where explicit feedback condition seems to emerge as the most preferred condition, with the robot being rated significantly higher in terms of understanding and adapting to what the participant said. Implicit condition performs the best at understanding how the participants might have felt, fulfilling the requirement from the robot under this condition. Finally, for appropriate rating as well, we see the adaptive conditions performing significantly better in terms of both robot positioning and speed. Our interaction with the participants post experiments also brought out interesting opinions about the waiter. In general, participants found the interactions to be enjoyable and interesting, despite repeating the same 4 tasks multiple times across the conditions. They all mentioned that they could imagine being served by a robo-waiter like this in the near future. Some participants expressed inhibitions to the robot approaching them face-on, terming them to be frightening, while the same participants felt the robot movements, particularly upper body movements, to be more human-like. To conclude, we present the first work investigating real-time adaptation strategies for robo-waiters to learn socially appropriate behaviors. We show that using crowdsourced annotations can provide a generalized understanding of what is considered appropriate. This understanding can be improved individually when interacting with individual users by factoring in explicit or implicit feedback. While explicit feedback seems to be better as it improves enjoyment, sociability, and adaptability for robot waiters. Next steps for us will include considering multimodal analysis of user behavior to capture implicit feedback, as valence alone might be insufficient to do so. Also, with COVID-19 restrictions hopefully lifting, we would want to extend our evaluations to a wider and more diverse audience, using more realistic restaurant settings involving food and other social aspects of the interaction. Finally, I'd like to thank our sponsors and my co-authors for their contributions, particularly Emily, who conducted these experiments as part of our MPhil dissertation. Thank you so much for listening.